You are already there only.
Uh,
Okay, sorry, na. I connecting with the
the
mobile.
answer coming.
Answer, you shared the answer, I think, na. Wait,
Yes.
wait. How much you are saying the answer?
57.4.
57.81, correct. This is the P total. You have to convert, find in the vapor phase also. You tell me in the vapor phase. P total is correct, 100% correct. Tell me in the vapor phase. Uh, uh.
So P vapor phase Y Y is P by this P total. That will be 42 by 57.5. The answer is almost 42 by 57.5.
This is the ethanol, methanol. Yeah. What I wrote, that is correct. All got deleted. This question was there only, no? So P total you are saying here already you have calculated P total. So P total portion I am not checking out.
Yes.
How much you are saying P total, Sanay? P total is equal to
57.
87 or 57?
57.
Wait, let me check again.
Sir,
50,
57.5.
57.8 they are talking. Okay, but 5 can be considered. Okay, this is the MMHG. MMHG. Now, what we are
Y for
asking,
ethanol is 0.73 and Y for methanol is 0.27.
Acha, you are telling the answer directly. Ethanol, you tell me again. Ethanol is 0. 0. Here, methanol, you tell me. Methanol, 0.52. Methanol, how much coming?
0.27. 0.27.
0.27. Let me check. So P ethanol, if you are going, so it will be, that is P not ethanol. No, P ethanol. P ethanol, this is going to be, and that is going to be P total. P ethanol, that is P not ethanol,
For what you are writing is not visible to me.
not visible to you, sorry. Now visible to you?
No visible.
So P not ethanol means what? P not ethanol, that is, if you are writing
But
P ethanol, not P not ethanol. This is P not ethanol you are writing. So this is X ethanol also, ETOH. So P not ethanol, how much is there? 42. And X ethanol, how much you got? X ethanol?
one.
X ethanol? 0.66. 0.66. Divided by P total. P total 57.8. Now you calculate. Now you calculate how much coming. So this is 42 multiplied by 0.66 divided by 57.8. So 0.47. You are telling wrongly. I don't know why. 0.47.
Now okay.
P ETOH is there, and P X ETOH, and that is X MOH is equal to 1. So X MOH you are writing. So 1 minus X ETOH. So 1 minus X ETOH. So 1 minus X ETOH 0.47. 0.47. So if you are solving 0.47, 0.52 around 0.52 is coming. Check. Correct, na?
Yes, sir.
Your father is doing prayer or what?
Yes, sir. Yes.
That is what sound is coming. Okay, this question number. You do this. Read the question. Don't write the question. I will share you. Not share you. I will say. I am sharing you right now only. It is there with me.
Liquid A is mixed with
Hmm.
3 mole of liquid B.
Hmm.
Assume
Hmm.
A plus B is an ideal solution.
Hmm.
If P naught A is 150 mm of Hg and P naught B equal to 200 mm of Hg,
Hmm.
calculate
Hmm.
so vapor pressure of A in solution,
Hmm. Hmm.
vapor pressure of B in solution, and the total vapor pressure of solution.
Are you doing this one? Are you trying or should I do?
You do say this type, I'm not able to do still now.
Still, you are facing the problem.
Hmm.
But we have done, na? Many problem we have done. Okay. So what they are saying in this question, if 2 mole of liquid A mix with 3 mole of liquid B, so Na they have given, how much they have given Na? 2 mole. Now Nb also given, how much mole they have given Nb? 3 mole. Okay, this one. Assume A and B is ideal solution. Okay, so P naught A they have given. P naught A, how much they have given? 150 mmHg. P naught B they have given 200 mmHg. They are, this is the mmHg. And here is also, this is going to be mmHg. Then calculate vapor pressure of A in solution, vapor pressure of B in solution, total vapor pressure of solution. So total vapor pressure. So PA is what is P naught A X A. This is only na. So P naught A, first one we are doing. First one we are doing. So here you see P naught A already they have given. P naught how much? 150. Multiply by XA. XA means NA divided by NA plus NB. So what it will be there? 150 multiply by Na. 2 mole divided by Na 2 plus 3. So 150 multiply by 2 upon 5. So 5 3 ja 15. 30 into 2. So it is coming 60 mmHg. 60 mmHg. The first one is okay. Now second one. Are you getting this one?
Hmm.
Uh, Simple, this is there, and PB is equal to P naught B XB. So PB they have given, that is 200 multiply by XB. XB will be how much? NB upon NA plus
120 is
NB.
coming.
Uh,
120.
120 is coming. Okay, good, 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 good. So 3 upon 5. So 5, 4. 40 multiply by 3. Thank you. So 120 mmHg. Now they are asking total vapor pressure. So PT is equal to P total you are going. So what is there? It is PA plus PB. So PA plus PB means 60 plus 120. 60 plus
180.
180 mmHg. But that much only asking. Two more question. Is it okay?
Yes.
Okay, next one you see. Okay, try this one. Hmm. This one. Can you?
Try.
Hmm.
Calculate the vapor pressure of a mixture containing 252 grams of N-pentane. N-pentane. What is the molar weight? Molar weight is 72 and 1400 grams of N is in. So what is this heptane?
heptane.
N-heptane. Molar weight 100. 20. So the vapor pressure of N-pentane and N-heptane for 20 ml. I can do this now.
Okay, then do.
So the formula for N-pentane is C5H12.
A formula is not required. Already molar mass given. So what we will do with the formula? Pentane, if you are writing pentane, suppose it is the pentane. So this is C5 and it is going to be 5 to H12. C5H12 means 12 into 5 plus 12. So 70. No, 60. 60 plus 12, that is going to be 72. So whatever given, that is correct. Heptane, you are going C7, H, how much? 16. So 84 plus 16, how much? It is 100. So no need to calculate, already given here now. Should I do this one? Should I do this one?
No.
Where you are doing? It is not visible to me.
What's on the screen? Sir? I was doing on the copy. That is.
No. You do here on the screen. Can't you do on screen?
I can do.
Do it here. You use the portion half, then half. Otherwise, it won't finished. Half here, then half here. Otherwise, you divide in 3 parts. Here, this portion also you can use.
What is the vapor pressure? What they are asking, vapor pressure of mixture.
252. Okay. Divided by 70. So 3K guys.
Sir, they are telling to find out the vapor pressure and then they are telling that already it is given. So that means you have to find the PA or P not A.
No, these are what they are. Calculate the vapor pressure of the mixture containing 252 gram of this pentane and this one 1400 gram of heptane. I think N heptane they have given. That is why it is the molar N heptane. At the vapor pressure are F and heptane and N pentane. This is the what
But you are
pressure?
saying that calculate the vapor pressure and then you are giving the vapor pressure also.
What vapor pressure? This is pure state. This is pure state now. These two are the pure state. Total vapor pressure. This is vapor pressure of N-heptane and N-pentane are given respectively. Calculate the vapor pressure of mixture. Vapor pressure of mixture, what is this? Total vapor pressure, na? Vapor pressure of mixture is total vapor pressure. Should I do?
So doing.
1400 upon.
So what I am doing is correct or not?
Yeah, correct only. Correct, of course, correct only.
35 for 20, 420 into 35 by 175.
Yes. 420 multiplied by 3.5 divided by 17.5.
84.
84, correct.
Now what to do for the total pressure? Total pressure is
112.8 is coming. Total pressure.
that will only comes 84 and 28.2. 84 means now. This is not the 0.8 here. 8 and 4, 12.
112. Yeah, correct. This is 112.8, correct. Unit is same, mmHg. Okay. What else they are asking? No, that is over. So you understood this problem. Let us move. You erase what you wrote. Can you erase this one?
Yes, I will.
Erase. Not able to erase, I think.
Sir, gone or not?
Not. That is everything is there only.
Okay. So now?
Going. There must be some option. Directly you can erase all. Here.
That one not work.
That is not going. Why it is not going? I think I need to refresh the screen.
Yes.
Now you try to erase.
Not going.
Not going. Then what we can do? From my side also it is not getting erased. Totally. Okay. Gone. So now you do this question. Can you try this?
Yes, sir. Vapor pressure of pure is 100 mm Hg and vapor pressure of pure B is 50 mm. 2 mole of A and 3 moles of liquid B are mixed to form this ideal solution. Form an ideal solution. What is the vapor pressure solution?
Should I do?
No, sir, I can do. Same problem only. Going around. Must be the 150 mm. P equal to 100 into what is given 2 mole of liquid and 3 mole of liquid.
So 3 mole of liquid B. Okay.
100 is 150. 150 into 3 by 5, 30. 90 mmHg. So, um, so done.
Done. 130. Your answer is coming 130, no?
Yes.
Here we have to check which question is that one. Let me see. Vapor pressure of pure liquid is. Let me find out the question first of. 130 mmHg, correct. Very good, very good. This is correct. Good. So already you are able to do this type of problem now. Okay, let me go back and see the one more problem.
Okay, another from this type, sir. Another from this.
Another from this type. Now already you did not 10, 20 questions. Many question you did. 10 question, yeah, I think you have done. So
No, no, sir, not 10.
not
3,
10,
4, 2, 3, 4, 5. 5 only.
5 only.
5 and 6. 6 we have done.
6 you did not. Okay. The 6 only having. Now there is no problem. I don't have the more problem. I will share you. Okay. So what you do now, the next point you see, come back to here, you see what are the next things which we can learn. NCRT. So just wait a moment. Let me download the NCRT one. Yeah. So yesterday the Raoults law we finished fully. We have finished Raoults law and Henry law. Both the law we have finished, right? Now, two types of solution also we have finished. That is the gas in liquid and liquid solution. Now we are going to deal with the solid in liquid. Solid in liquid. So let us try to see here solid in liquid what we can do. So Raoult's law as a special case of Henry law. What is this Raoult's law special case of Henry law? Can you tell me what is the Raoult's law, a special case of Henry law? What do you mean by this?
Crowd flow is a special case of Henry law in which the cage becomes equal to the P1 naught.
P1 naught. What is the P1 naught?
So P1 naught is the vapor pressure of the first component.
Vapor pressure in the pure state. Vapor pressure in the pure state. This is
The
P1
pressure
naught.
of the first
Okay. Now here see vapor pressure of solution of solid in liquid. We are talking about solid in liquid. Firstly, I am dealing the NCRT. Then I will tell you. Okay. Here is what is there.
yes.
Solid in liquid. Solid in liquid. Solid in liquid. Okay. This is this thing. So some basic idea is there that you need to know. Okay. What the most of the solid. Most of the solid. Most of the solids are non-volatile. What is they are taking? Non-volatile. What do you mean by non-volatile? That is, do not have vapor pressure. Do not have vapor pressure. In other word, you can say they are not vaporized. They are not vaporizes. Okay. Like you are having sugar. Sugar is not going to vaporize. Do not have vapor pressure. Okay. So is this point is clear to you?
Yes, sir.
Now, second one, liquid have vapor pressure. Liquid are volatile. Yesterday already I told you, liquids are volatile. Volatile. Liquid are volatile means they can be vaporized. That is, they have what we can write. They have vapor pressure. VP. VP means vapor pressure. These two things you need to keep in mind. Now, what we are talking about here, you see, this we are talking about the pure liquid we are dealing. If I will talk about the pure liquid, this is the pure liquid A, pure liquid. So pure liquid means it is having high vapor pressure, high vapor pressure. Now, I am taking another one, taking sugar solution. I am taking which one? Sugar solution. Solution. Sugar solution means solid sugar, solid sugar. Sugar means solid sugar in water, in liquid water, in liquid water. Now, here, when the solution is being formed, you will find that is everywhere particle will be same. In the solution, particle will be same, yes or no?
Yes.
Okay. And so what will happen? This is the closed system we have considered, and particle will be same throughout. That is why homogeneous mixture. So with the black sign, we are putting here the particle of the sugar. Will the sugar particle vaporize, Sanoy?
No, sir.
No. So what it is going, but it is there on the surface now. What will go, what it is going to do, it is going to suppress the whatever the liquid particle vaporize, because it is present on the surface, whatever the liquid particle going to vaporize, they will come back again. So here if you see in the diagram, so what you will going to find here, more in this case, more vapor particles will be there, because the surface contain what? The vapor. All the pure liquid means high vapor pressure means all particle vaporize. Pure liquid means all particle vaporize. Yes or no? All particles
Yes.
vaporize. So vapor pressure will be more. All particle vaporizes. Sugar solution, only liquid vaporize. Only liquid vaporize. Only liquid vaporize. And that on the surface also what are there? Solid particles are there. So vapor pressure will be very less. Yes or no?
Yes, sir.
So vapor pressure, if you are calculating the vapor pressure of this case, so what we can write, the P A is equal to P naught A X A, and PB, there will not be PB. No. If you are talking about XB equal to solid, solid means do not have PB. Do not have PB. It cannot vaporize. No, solid cannot vaporize. So here you have to apply only this formula. Only one equation will be there. For what? For solid in liquid. For solid in liquid. Because solid is not going to vaporize, only liquid. Now let's come back and read the NCRT and try to understand what the concept is here. Another important class of
PP or PP?
whatever you can consider here, may solvent. The aim is solvent. Here is, if you are writing A is solvent, no, so I am considering this is solvent. It is depending only on the solvent, no. Solute is the no vaporize. Solute is not vaporize here. Only liquid vaporize. Solid in liquid,
Hmm.
solid do not vaporize because they are not having vapor pressure. Now is it okay?
Yes, sir.
Come back here. Here. So we are going to deal this one. Third type of liquid we are dealing now. Another important class of solution consists of solid dissolve in what is liquid. For example, sodium chloride, glucose, urea, cane sugar in water, and iodine, sulfur dissolve in the carbon disulfide. Some physical properties of these solutions are quite different from those of the pure solvent. Okay, if you talk about pure solvent, the solution is having different, because pure solvent, see the vapor pressure, how many are particles are there? 2 to 4 to 6 to 8. Here, solid in liquid, only 4 particles. So vapor pressure will be, for example, vapor pressure. For example, vapor pressure will be what? That is different. Getting this one.
Yes, sir.
Vapor pressure will be different.
Lesser, lesser.
Lesser. So we learn in unit 5, class 11, that liquid at a given temperature vaporizes under the equilibrium, means evaporating equilibrium condition. The pressure exerted by vapors of the liquid over liquid is called vapor presses. The study we have done this one. The pressure exerted by vapors of liquid over liquid surface is called vapor pressure. Now here you see 2.4a. This is the A. In pure liquid, the entire surface is occupied by molecule of liquid. Total is what? Molecule of liquid. So totally vaporizing, to more vapor pressure. Non-volatile solid is added to solvent. Given solution. Non-volatile, this one. This one, green color one. This is non-volatile, means solid particle. Okay. In the B diagram, you see the vapor pressure of the solution is solely from the solvent alone. So what is slow? Vapor pressure is less than the pure solvent. Again, the vapor pressure of the solution at given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. Are you getting this?
Yes, sir.
In the solution, the surface has both solute and solvent molecule. So solute and solvent both are here. Thereby, the fraction of the surface covered by the solvent molecule gets reduced. Solvent molecule, how many are there? One, two, three, four, five only. Consequently, the number of solvent molecule escaping from the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. Getting?
Yes, sir.
Okay, now this one. The decrease in vapor pressure of solvent depends on the quantity of non-volatile solute present in the solution. So more the quantity of non-volatile solute, solid solute is there, more will be decrease in the vapor pressure. Okay, so that is what? The decrease in vapor pressure of solvent depends on the quantity of non-volatile solute in solution, irrespective of its nature. For example, decrease in vapor pressure of water by adding 1 mole sucrose to 1 kg of water is nearly similar to that produced by adding 1 mole of urea. So this is depending on different condition. The same quantity of water at the same temperature. So let us try to read here this point. Here, the important is this one. What the point is there? Raoults law in general form can read this. Can you read
Yes, sir.
some?
Yes. Sir, after this one, the Raoults law in general form can be stated as for any solution, the partial vapor pressure of each volatile component in the solution directly proportional to its mole fraction.
Hmm. Now this line, this is the study one. This line is study one, same. For a solution, the partial vapor pressure of each volatile component. Which one they are talking? Liquid component, not the solid. In the
Yes.
solution is directly proportional to its mole fraction. We are not talking about the non-volatile. We are talking about the volatile only. Now, here you see, in binary solution, let us denote the solvent by 1. Solvent by 1. Getting? So just now you asked no 1 or 2. So this is solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecule are present in the vapor phase and contribute the vapor pressure. Now these are very important. You understand this line. Are you getting this line?
Yes, sir.
Because second is solid na, so it is not going to contribute in the vapor pressure. No contribution in vapor pressure. Only which one is having the first component. Now let P1 be, they are saying let P1 be the vapor pressure of solvent and X1 be the mole fraction and P not be its vapor pressure in the pure state. Then according to Raoult's law, P1 proportional to X1. So P1 is equal to P1 not X1. The proportionality constant in equation to the vapor phase a pure solvent P naught 1, a plot between the vapor pressure and mole fraction is this one. So here, this is the solvent only. Here solvent equal to x1 is equal to 0 and x1 is equal to 1. So when the mole fraction increases, so vapor pressure is also going to increase. So vapor pressure of pure solvent. This is like, yesterday we did this one. Are you getting this?
Yes, sir.
Okay. Here, ideal and non-ideal solution we did study. Ideal and non-ideal solution.
There is no difference. Yes.
Difference also we have done. So what you do, you read this ideal and non-ideal because we have already discussed this one. So if you read this one, automatically it will be clear to you. Okay, you read this one, and wherever you are not able to, I will explain. You read this one because my throat is started. It is irritating. Okay, read this one. Read loudly.
Liquid solutions can be classified into ideal and non-ideal solutions on the basis of Raoults law.
Hmm.
Solutions which obey Raoults law over the entire range of concentration known as ideal solutions.
You
And the
explain also.
ideal
You
solutions
explain also. You are very fast. You are reading. I can't understand. Hmm. You explain
solutions
also.
which obey Raoults law over the entire range of concentration is
Hmm.
ideal solution. They
Hmm.
have two other important properties. There is H del H mix is zero, del V mix is zero.
Hmm.
It
Hmm.
means that the heat no heat will be absorbed or given out when the components will be mixed. So
Hmm.
thus a volume will be equal to the sum of volumes,
Hmm.
and the molecular level ideal behavior of the solutions can be explained by
Hmm.
considering two components A and B. There
Hmm.
in pure one, the intermolecular attractive forces will be of type
Hmm.
AA, BB, and
Hmm.
in binary it will have AB and AB. So, sir, if the intermolecular forces AA, BB are nearly equal to those between A and B, so,
Hmm.
sir, this leads to the formation of ideal solution. A
Hmm.
perfectly ideal solution not available and mostly rare, but some solution nearly ideal,
Hmm.
like N-heptane and N-heptane solution, bromoethane and chloroethane solution,
Hmm.
benzene and toluene solution, and they fall into this category.
Hmm. So understood this one.
Yes, sir.
What? Why? If you, I will ask you. Here, this one N-heptane and N-hexane. Why they are ideal solution? Why they are ideal solution? What the reason will you give? Like another is
So
bromoethane.
they were following the route. So they are following the routes at all the concentrations. And so
Uh,
their AA, BB, and HB are almost equal. And
uh,
their A del H mix is equal, del V mix is equal.
okay, because similar interaction are there. Similar interaction. Okay, similar interaction. So similar interaction means AA equal to BB equal to what is AB interaction. Na? So the vapor pressure will come automatically same. And that is P total will be same as how much? Expected from which law? Expected from which law? Raoult's law. Raoult's law. Delta H mixing will be how much? Zero. Means no energy will be liberate. Here you see for the enthalpy of mixing of the pure component to form solution is zero. Okay, this one is zero. No heat release, no heat absorb. Volume of mixing will be zero. There will not be any change. Okay. So delta B mixing will also be zero. Are you getting this?
Yes.
Okay. Now we are dealing the non-ideal solution. Let us be the non-ideal solution here. Non-ideal solution. A non-ideal solution. Can you define what do you mean by non-ideal solution?
Non-ideal solution don't follow the routes at all the
Don't follow.
concentrations.
Thank you.
They
Thank
are
you.
exhibiting positive deviation or negative deviation. And
Don't follow Raoult's law. Okay.
P
Why don't
total not
follow why don't follow Raoult? Because A interaction not equal to BB interaction not equal to
equal to any
AB
fraction.
interaction. Okay. So because of these things, they don't follow Raoult's law. Okay. Now there
Yes.
is two possibilities are there. What can be there? One more thing is there. Delta H mixing, if you are mixing, it is not equal to zero, and delta V mixing, it is not equal to zero also. These things. Now, what we are going to do here, Tanoy, that is, in what case, suppose this one, if vapor pressure, I'm writing in the different way. So, this one non-ideal solution are two types. Non-ideal solution are two types. One is the positive deviation. One is positive deviation, and second one is negative deviation. Deviation from. Can you tell me from?
The positive deviation from the ideal vapor pressure.
That is
From
Raoults law. Raoults law. Raoults law. Getting this one from Raoults law. A positive deviation, when it will come? Positive, more vapor pressure. In this case, more vapor pressure will come. And in this case, what is there? Less vapor pressure. Okay. So here you read, that is little bit in detail. Here is this one is how much? Positive deviation. Okay. And this is the negative deviation. Negative deviation. Okay, this is what are the points are that we are going to mention. First point, okay, vapor pressure of solution. Vapor pressure of solution is more than expected from Raoult's law. Expected from Raoult's law. Raoult's law. And here is vapor pressure of solution. Vapor pressure of solution is less than what is Raoult's law. Raoult's law. Now, point number 2. A, this interaction we are talking about. Here interaction. See, more vapor of pressure are there. So again I am writing here AB. AA, BB. These are interaction. This is solute, solvent, solvent. Or this is the solvent if you are considering solvent, solvent, and this is solute, solute. So when you are mixing, what type of interaction will form? A, B. This is the solvent and this is going to be solute. So this interaction is weak. This interaction is weak. So since this is weak interaction, so more evaporation will take place. Yes or no?
yes.
So if solute solvent interaction is weak, so the more vapor pressure. So high vapor pressure. So high vapor pressure. Now here you see A, B and BB is the A and BB is there. If you are mixing this one, it is going to be AB. This is strong. In case of negative deviation, is strong interaction. If it is strong interaction, so it will hold together. It will hold together means it is not going to vaporize. So not vaporize means low vapor pressure. Got it?
Yes, sir.
Okay. Next one. Delta V mixing. Delta V mixing will be greater than 0. Delta V mixing will be greater than 0. And delta V mixing will be less than 0. Getting? Yes, yeah, no?
Yes, sir.
Okay. Next one. Here a hydrogen bonding can operate. No? Is strong. They are saying is strong. Hydrogen bonding. Strong hydrogen bonding can operate. Can operate. Operate. No. Weak. Here the no. Where strong hydrogen bonding will be the in which case? Negative deviation. Na? Here strong H bonding may operate. H bonding may formed. Where? Between solute and solvent. Between solute and solvent. Solute and solvent. These things you need to keep in mind. So let us read the NCERT for better understanding here. So when a solution they are talking about, So when a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solution. So you got to know no, ideal and non-ideal. The vapor
Yes.
pressure of such solution either high or lower than predicted by the Raoult's law. If it is higher, the solution is exhibited positive deviation, and if it is lower, it is exhibited negative deviation from the Raoult's law. The plot of vapor pressure as function of mole fraction for each component shown in figure 2.6. Okay, so 2.6 we can see here first one. See, here is the positive deviation. First one is what they are talking about, solution showing positive deviation. This case is for the ideal. This is the ideal case. This one is the ideal. Dotted one is ideal. Getting dotted one is ideal.
Okay.
But it is found that when you are mixing, so if interaction is less, so you see both the vapor pressure are what? This is solvent is more, solute is more, and total adding, that is it is also coming more. Second case, this is the ideal case. These are the ideal case. But now after mixing it is forming the bond, so it become the weaker. So vapor pressure is coming less than the expected from Raoult's law. Yes, yeah, no.
Yes, sir.
Okay. So this diagram is very easy. I'm not going more detail. The cause of these deviation, very important, no? Very, very important. Deviation lie in the nature of interaction at the molecular level. In case of positive deviation from Raoult's law, AB interaction are weaker. What they are saying? AB, solute solvent interaction are weaker. In which case? Positive deviation. Just now I explained, no? Then those of AA and BB. Are you getting this?
Yes, sir.
In this case, the
Positive deviation interaction because that's quenching of.
intermolecule, okay, solute solvent molecule are weaker than those of between solute solute, solvent solvent. This means that in such solution, molecule of A and B find it easier to escape than the pure state. This will increase the vapor pressure. Is it okay? Yes or no? Hello?
Yes, sir. Okay.
Pressure and result in the positive deviation. Example, here we are talking example. Ethanol and acetone behave in this manner. In pure state, ethanol molecule are hydrogen bonded. On the other hand, acetone in its molecules get between the host molecule and break some of the hydrogen bond between them. So acetone molecule break the hydrogen bonding of the alcohol. Due to weakening of interaction, the solution show positive deviation from Raoult's law. Okay. So this diagram we have explained. In this solution formed by 18 carbon disulfide to acetone, the dipolar interaction between solute solvent molecule are weaker than the respective interaction among the solute solvent and solvent solvent molecule. This result also show the positive deviation. So which one? Carbon disulfide to acetone. This is also example of two example we are adding. What is acetone plus alcohol. Alcohol that is positive. And second one, what is there? Acetone plus what is there? CS2 carbon disulfide positive. Now you see this one. Second case also very important. See this one. In case of negative deviation from Raoult's law, the intermolecular attractive force between AA, BB are weaker than those of between AB and leads to decrease in vapor pressure, resulting in negative deviation. An example of this type of mixture, phenol and aniline. Okay, so AB interaction become stronger. Phenol and aniline, hydrogen bonding they form. In this case, intermolecular hydrogen bonding between phenolic proton and lone pair of nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between similar molecule. So that is phenol and aniline form the stronger hydrogen bonding. So that is negative deviation. Similarly, they are saying a mixture of chloroform and acetone form solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with acetone molecule. Now you see the acetone and this is chloroform. So this is what is in between they are forming hydrogen bonding. So this is the negative deviation. Next one, see. This decrease in escaping tendency of molecule for each component, consequently, the vapor pressure decrease resulting in negative deviation from Raoult's law. Got it?
Yes.
Now, very important point, azeotropic mixture. Azeotropic mixture. Azeotropic mixture. What is the azeotropic mixture? That boiling point of the mixture is same. Boiling point is same. But suppose A and B two are there now. So they are forming AB solution. So BP of A and B are become same. So become same. So when the boiling point of the two mixture becomes same, that is called azeotropic mixture. Now you read, then it will be more clear to you. Okay. What is some liquid on mixing form azeotropes, which are binary mixture having same composition in liquid state, vapor state, and boil at constant temperature. Boil at constant temperature means same temperature. So you read this line. No, azeotropic mixture, very, very, very
Yes, sir.
important. Okay, so they are saying that is in the liquid state or vapor state, same composition. So in the both the state, if the same composition is there, it means boil at the constant temperature, same temperature. In such case, it is not possible to separate the components by fractional distillation. If both are boiling by at same temperature, how can you separate? If the boiling point difference is more than 20 degree, 10 degree, then you can separate now. But if it is the same, you cannot separate. Getting my point?
Yes, sir.
Okay. Now the second point you go. Second point. What the second? There are two type of azeotropic called minimum boiling azeotrope and maximum boiling azeotrope. Okay. So minimum boiling azeotrope means boil at low temperature. Minimum boiling means boil at low temperature. Maximum boiling means boil at high temperature. This is there. The solution which show large positive deviation from Raoult's law form minimum boiling azeotrope. So you may find here difficulties. So what I'm doing, I am sharing this one, taking the whiteboard here. You see. So here you see non-ideal solution. Non-ideal solution. Non-ideal solution is there. Okay. So in this case, non-ideal solution are two types. Positive deviation. One is positive deviation and second is negative deviation. Negative deviation. Positive deviation means high vapor pressure. High vapor pressure. And negative means low vapor pressure. So high vapor pressure means boil at. If vapor pressure is automatically high, boil at low temperature or high temperature? Tell me. Boil at. If vapor, like the petrol is there,
Low temperature.
vapor pressure is high. So it is going to boil at high temperature or low temperature?
Yes, sir.
Huh?
Low temperature, sir, lower one.
Boil at low temperature. Boil at low temperature. Boil at high temperature. High temperature. Okay. Now, if it is boiling at low temperature, so formed. What it is formed? Formed minimum boiling azeotrope. Boiling azeotrope. And form, what it is going to formed maximum boiling azeotrope. Maximum boiling azeotrope. Azeotrope. Now read again here. Read again. Positive deviation. High blood pressure, boil at. So which liquid will form the minimum boiling azeotrope? Can you tell me? Positive deviation or negative deviation liquid?
Positive deviation.
And which will form maximum boiling azeotrope?
Negative deviation.
Now come back to the slide. Here. Where is the slide here? Here. So this side. The solution which so large. Oh. See the point. Here they are saying. Now here. The solution which show large positive deviation from Raoult's law form minimum boiling azeotrope. Are you getting this?
Yes.
At a specific composition. Now come back here. For example, ethanol water mixture obtained by fermentation of sugar on fractional distillation gives solution containing approximately 95% by volume of ethanol. So 95% what is ethanol is there and 0.5% what is there? H2O. So this type of mixture they are forming that is having the same composition in liquid state and vapor phase. So they will boil at the same temperature. Once this composition known as azeotropic composition has been achieved, the liquid vapors have the same composition and no further separation occur. Second one, the solution that show large negative deviation from Raoult's law form maximum boiling azeotrope at a specific composition. Nitric acid and water is example of this class of azeotrope. This azeotrope has the approximately composition, the 68% nitric acid and 32% by mass of the water. So which one solution? Negative deviation. Negative deviation is forming maximum boiling azeotrope. Is it okay to you?
Yes.
So this is all we cover. That is the about the Raoult's law. Total covered. Now next topic is colligative properties. Now let us see some of the point here. Ideal and non-ideal we have already covered. Ideal and non-ideal. This one you already knows. This is already there. Give the region of formation of ideal bond. Ideal solution, similar type of interaction. Non-ideal solution, different interaction. Here you see this one. P total will be more than ideal. That is positive deviation. P total less than the ideal. That is negative deviation. Is it okay? So no.
Yes, sir.
This is the diagram. These are I am saying the previous year question. Here sign you see sign very important one. Not that questions are there, not important. Question. Enthalpy change, endothermic heat evolvement. These are examples are there. I will share you the examples. Okay. This example 58 one. They ask that is ethanol acetone forming what type of? This is positive deviation. Carbon disulfide, this is positive. Phenolaniline, negative. Chloroform acetone, negative. So you need to explain that is why negative. So this one you can read this one. If you are reading this one, you will get to know. Okay. So all are there.
Sir,
So this is I will share you the slide, this one. Okay. If you want to read, you can read also. Why is the absolute 100% ethanol cannot be prepared, but cannot be prepared by fractional distillation of ethanol water because they are forming azeotropic composition. So that is why. So these I will share. 9:30 you connect. 9:30 p.m.
right, sir? Yes, sir.
9:30. 9:30. Okay. Bye na.
Okay.
Hmm.
Yes.
You read all the points.
Okay, okay, sir.